Number 58. A 2-meter tall basketball player is standing on the floor 10 meters from the basket, as in figure P358. If he shoots the basketball so that it goes through the hoop without striking the backboard, the height of the basket is 3.05 meters. So first we're going to draw a diagram. We know that we already have a diagram, which is very beneficial. We're already solving. So therefore, we can just use the information that's already given to plug some in. Well, first, we know that the distance between the player and the basket is 10 meters. We also know that since the player is 2 meters high, the entire kinematic function and everything that's occurring is actually happening at this level here, meaning all this below it is relevant. So we're only looking at how the speed is right here until how it goes into the hoop, specifically without hitting the backboard. So we're only looking for this. So these 2 meters are relevant, making it only 1.05, where we subtract the height of the hoop with the person's height. We know that since the ball must be going at a constant velocity across on a horizontal, that it's going to have 0 meters acceleration. And we know that acceleration due to gravity within the y is negative 9.8 meters per second squared. Now with this information that we already have and that we've interpreted, let's look towards the angle that we're given. We know that we're trying to solve for the initial velocity from the ball as of right here. That little, how much or how hard the ball is thrown to get into the hoop. So we know that this is what we're trying to solve. So we can actually interpret both sides here using sine and cosine. So accordingly, the sine of 40 degrees would be opposite over hypotenuse, which would only equal initial velocity times sine of 40 is the opposite. And accordingly, we can do the same for this angle, or this vector right here, in order to solve for cosine 40 degrees is adjacent over initial velocity, which equals initial velocity times cosine of 40 degrees is the adjacent. So we can plug that in here. And as already shown, it's already plugged in as follows. We know that the initial and the final velocity when you're moving horizontal will be the same. Now that we have these values, we can think about plugging it into a kinematic. However, we're missing a value. We don't know the time. See, if we're trying to solve for time here, in order so we get a parallel here on the x and the y, we're going to come with a quadratic, and we don't want that. So we have to think about what is time in general. We know that time in velocity is velocity equals distance over time. And accordingly, we know that during the horizontal, everything stays constant in regards to the velocity. I mean, the velocity in that statement does not change. Therefore, we can start plugging that in. We know that in this case, that on the horizontal, we know that it's between the player and the basketball is 10 meters. And we know the actual velocity stays the same and will be constant. We can't plug in the y because the initial and the final velocity is different. And accordingly, we're going to get a different number if we plug in this value as our velocity. But since we know that this stays constant and that he's constantly 10 meters away throughout the entirety of the shot, we know that we can plug these values in to actually solve for our time. So we bring the time here, bring the velocity down here, and accordingly we get 10 meters over initial velocity cosine 40. And when you plug everything into the calculator, you find that time is actually equal to 13.1 over initial velocity. So now we have our time, which stays constant between the horizontal and the y. Now we can actually solve, since we have only one variable we're solving for. So we can plug all this in. I mean, easiest probably using the y, since we don't have the same here. We can easily plug into the y in order to find that initial value on how fast the ball is moving when it releases from the basketball player's hands. Accordingly, we can use change in x displacement equals initial velocity times time plus 1/2 acceleration squared. And when you plug those values in, we use 1.05 from here, and then the initial stated over here, and then times the time, which you just found. And we only get one variable that we're trying to solve for. If we eventually just plug everything in, end up getting 10.7 as our initial velocity. Thank you.